I'm André Zenner, and I'm a doctoral researcher at the German Research Center for Artificial Intelligence in Saarland University in Saarbrücken, Germany. In the following, I'm happy to present the TVCG paper of my co-authors Christine Ullmann, Antonio Krüger, and me about combining dynamic passive haptics and haptic retargeting for enhanced haptic feedback in virtual reality. Our paper is concerned with two central challenges of proxy-based haptics for VR, a concept which leverages physical proxies to deliver haptic sensations during interactions with virtual environments. To achieve high-quality feedback, systems that employ proxy-based haptics need to solve the challenge of similarity by ensuring haptic probes are sufficiently similar in terms of their haptic properties to the virtual objects they represent. Moreover, they need to solve the challenge of collocation to enable seamless interaction. In our investigated proof of concept scenario, we consider a VR system that uses proxy-based haptics to render the weight distribution inside a virtual stick. Our paper proposes and evaluates the combination of two different techniques for enhancing proxy-based haptics that each have individually been shown to successfully tackle the challenges of similarity and collocation, but have only been studied in isolation in the past. The first of those techniques is dynamic passive haptic feedback, short DPHF. The idea of this hardware-based approach is to equip proxies with simple actuation in order to adapt their passive haptic feedback properties such as their shape, or in our case, their internal weight distribution, implemented by a weight-shifting tubular proxy. The second technique we consider is haptic retargeting, short HR, a software-based approach that utilizes hand redirection to let users touch proxy objects at offset grasp locations. The central question guiding our work is whether the combination of both of these techniques can better solve the challenges of similarity and collocation than the individual techniques can do alone. To answer this question, we explore in our paper four basic conditions in the performance in rendering weight distribution inside a virtual stick. A baseline condition not employing any of the two rendering strategies. A second condition dynamically shifting a weight inside the proxy. A third condition unnoticeably redirecting the user's grasp away from the passive proxy's center of mass. And a fourth condition combining dynamic passive haptics and haptic retargeting by shifting the weight inside the proxy towards one end while redirecting the user's grasp towards the opposite end. To implement these conditions in a controlled user experiment with 24 participants, we used Shifty, the weight-shifting proxy presented in our 2017 TVCG paper, and the popular hand redirection technique by Chang and colleagues within the unnoticeability ranges found in our VR 2019 paper. As a metric for assessing the performance of the different rendering techniques in tackling the challenge of similarity, we identified the maximum conveyed virtual lever as a suitable measure since it represents the number of different virtual objects the system can provide appropriate feedback for. Concerning the challenge of collocation, we identified the amount of maximum spatial offset between the proxy and the virtual object that still goes unnoticed by users as a suitable metric. When grasping a virtual stick represented by a misaligned prop, users might perceive an imbalance which, if not matching the virtual object, can negatively influence the experience. By using the different haptic rendering techniques, such unintended perceptions can be compensated for. We conducted a first user experiment to compare the maximum virtual weight shifts that can be conveyed. As shown in this video here, users repeatedly grasped a virtual stick at its center, lifted it up, and indicated in VR where they perceive the stick's center of mass to be located. Our results show that the combined rendering technique is capable of conveying a significantly greater range of weight shifts than the individual techniques alone can convey. In a second psychophysical experiment, we employed an adaptive interleaved staircase method to assess how much spatial offset between physical proxy and virtual stick along the stick's main axis can go unnoticed. Or in other words, for how much unintended weight shift as a consequence of proxy misalignment the techniques can compensate for. This required participants to repeatedly lift a virtual stick that was expected to feel balanced and to indicate if any imbalance was perceivable. While misalignments of 5 centimeters were already perceivable when no compensation was applied in our baseline condition, misalignments of 10 centimeters were still unnoticeable with the combined rendering technique. The findings of our second experiment thus validate that when a dynamic prop and haptic retargeting are combined in our investigated scenario, significantly more spatial offset between proxy and virtual counterpart can remain unnoticeable compared to what can go unnoticed when compensating for it only with the individual techniques or not compensating for unsuitable perceptions at all. We would like to note that our investigation serves as a first systematic exploration of how dynamic passive haptic feedback and haptic retargeting can be combined and still is based on certain assumptions. For example, only offsets along the stick's main axis were considered and only the haptic dimension of weight shift. In future work, we aim to explore how the benefits of combining DPHF and haptic retargeting generalize to further scenarios and haptic properties. Moreover, the data in our experiment indicates that users seem to systematically overestimate weight shifts in VR, an observation that merits further investigation in future experiments. For more details about our work, please refer to our paper. Thank you.